In this part of the lesson, I'm going to look at comparing slopes. I'm going to start by looking at perpendicular lines. Then we're going to talk about vertical lines and horizontal lines. And I'm going to end with a summary of the types of slopes we've talked about and a couple of examples. So let's start with perpendicular lines. Two lines that meet at a right angle, provided the scales are the same, are called perpendicular. In this diagram, the green and purple lines are perpendicular. The horizontal and vertical axes are also perpendicular. Let's find the slopes of the two perpendicular lines given in this diagram. So starting with the purple line, let's say I take these 2 points right next to one another. It looks like I have a rise of -1 and a run of 1. So the slope of the purple line, I'll call this m sub p, is rise over run, -1 over 1, which is -1. Now let's look at the green line. If I take these 2 points right next to one another, it looks like I have a rise of 1 and also a run of 1. So the slope of the green line, rise over run, is 1 over 1, which is 1. What is the product of these two slopes? Well, if I take the slope of the purple line and multiply it by the slope of the green line, all that I'm multiplying is -1 times 1. And this is -1. Let's try that for another pair of lines. The lines in this diagram have already been labeled with slope triangles for me. Let's start by looking at this purple line, which looks like it's decreasing. My run looks to be 1, 2, 3, 4, 5. And my rise, since it's downwards, is going to be negative. In particular, -1, -2. So the slope of the purple line, rise over run, would be -2 over a run of 5. Well, let's look at the green line. The green line looks to be increasing. Starting from the same point as I started on the purple line, it looks like I have a rise of -1, 2, 3, 4, 5, and a run of -1, -2. So the slope of the green line, m sub g, is going to be a rise of -5 over a run of -2. Negative divided by negative is positive, so the slope is 5/2. Well, let's think again about the product of these two slopes. What do I get if I multiply the slope of the purple line by the slope of the green line? Well, now I'm multiplying -2/5 by 5/2. A negative times a positive is negative. 2 times 5 is 10, and in the denominator, 5 times 2 is also 10. 10 divided by 10 is 1. So the product of the two slopes is -1. That's the same product of the two slopes I got in the previous example. One other thing I want to look at before leaving this example is comparing these two slope triangles. If I look at the slope triangle for the decreasing purple line, it looks like I have a run of 5. The run seems to be the same length as the rise for the green line. Although the rise on the green line is negative, the run on the purple line is positive. Looking at the rise on my purple line, the rise was -2, seems to have the same length as the run on the green line. Let's see if we can see this a little bit better. I'm going to take the purple line and rotate 90 degrees to the left. When this happens, we see the run on the purple line becomes the rise downwards on the green line. And the rise on the purple line becomes the run on the green line. Let's look at one more thing here. I mentioned that my rotation was a 90-degree rotation. So I know that looking at this angle that I have a measure of 90 degrees. So if I call this smaller angle at the top A and this larger angle at the bottom B, I know that the sum of the measures of these two angles is 90 degrees. When I rotated the diagram, I saw that the two slope triangles lined up. So this small angle A above is exactly the same as this small angle A down below here. So if I look at angle A at the bottom here plus angle B, the sum of the measures of these two angles is also going to have to be 90 degrees. So the angle between the green increasing line and the purple decreasing line is 90 degrees. The two perpendicular lines meet at a 90-degree angle. An important condition here, though, is that the scales on the axes are the same, and they were in this setup. So let's summarize. We have a property that says if the product of the slopes of two lines is -1, then the lines are perpendicular. We can also say that two non-vertical lines are perpendicular if the slope of one is the opposite reciprocal of the slope of the other. Well, let's look at some examples to make sure that we really understand what it means to be an opposite reciprocal. Here I'm starting out with the number 3/4. In my table, I also want to write down the opposite reciprocal and then the product of the number and its opposite reciprocal. Since the number 3/4 is positive, I know that the opposite of it is going to be negative. We're looking for an opposite reciprocal, though, so I also need to take the reciprocal of 3/4. The reciprocal of 3/4 is 4/3. So the opposite reciprocal of 3/4 is -4/3. When I multiply these two numbers together, a positive times a negative is negative, and I have 3 times 4, 12 in the numerator, and 4 times 3, 12 in the denominator. 12 divided by 12 is 1. So the product is -1. Let's look at another number. What if we started with the number -7? To find the opposite reciprocal, first I can think about the opposite. -7 is a negative number. The opposite of a negative number is a positive number. So I know the opposite reciprocal will be positive. I also have to take the reciprocal of 7. The reciprocal of 7 is 1/7. So the opposite reciprocal of -7 is 1/7. Once again, if I multiply these two numbers together, negative times a positive is going to be negative, and I'm going to have 7/7, which is 1. So the product is -1. Well, let's look at some examples working with perpendicular lines. In this example, we're asked to draw a line through the given point that's perpendicular to the line graphed below. So I've got this purple line, which looks to be an increasing line if I read it from left to right, which is how I want to read graphs, and I've got a point on the line. I'm asked to draw a line through this given point that's perpendicular to the line that's already graphed. Well, what do we know about perpendicular lines? What we just discussed is that perpendicular lines have opposite reciprocal slopes. So it would make sense here to figure out what's the slope of this purple line. So let's start there. Let's locate a couple of points on this line. It looks like I have a vertical intercept of 0, 3, and another point over here looks like 3, 4. So thinking about the slope, to get from 3 to 4, I have a rise of 1, and to get from 0 to 3, I have a run of 3. So the slope of this purple line that's graphed here is rise over run, a rise of 1 over a run of 3. The slope is 1/3. So what's the negative or the opposite reciprocal of 1/3? 1/3 is a positive number, the opposite is going to be negative, and I have to take the reciprocal of 1/3. The reciprocal of 1/3 is 3. So the opposite reciprocal of 1/3 is -3. So what I want to do is draw a line which has a slope of -3, passing through the point that was given to me. And the point given to me is -3, 2. So starting at this point, I want to think of a slope of -3. In fraction form, I could use -3 over +1. That would mean a rise of -3, so I'd want to move down 1, 2, 3 units, and right 1 unit. And let's do that again. Down 1, 2, 3 units, and right 1 unit. So now I'm going to get out my straight edge and sketch a line through the 3 points that I have. If I look at the scales on my P and Q axis in this case, it looks like I have equal scales. So the 2 lines that are now on the diagram should appear to meet at a right angle. The angle between these 2 lines should be 90 degrees. Let's look at another example. Same directions. We're asked to draw a line through the given point that is perpendicular to the line graphed below. This time, the given point is not on the line. Shouldn't matter though. Same steps as the last problem. I need to look at the line that's given to me, figure out what its slope is, and then determine the opposite reciprocal of that slope. So let's find a couple of points on this line. Looks like I have one here at -4, 6. And another one at -3, 4. To get from this top point to the lower point, looks like I have a rise of -2 since I moved downwards, and a run, which is positive since I'm moving to the right, of 1. So the slope of this green line, I'll call it m sub g, rise over run would be -2 over 1, which reduces to -2. So now I need to think about what is the opposite reciprocal of -2. Since I need to take the opposite, -2 is a negative number. The opposite of a negative number is a positive number. So I know my result will be positive, but I also have to take the reciprocal of 2. The reciprocal of 2 is 1/2. So the opposite reciprocal of -2 is positive 1/2. So starting from the point that was given to me in the diagram, I need to draw a line that has a slope of 1/2. So I need to locate some other points using the slope of 1/2. So just using the fraction 1 over 2, I could move from this point up 1 unit, a rise of 1, right 2 units, a run of 2. That gets me to the point 4, 5. Let's do that again. A rise of 1, a run of 2. That gets me to the point 6, 6. So now, using my straight edge, I want to sketch a line through these 3 points. Again, these axes are set up with equal scales, so it should look like the 2 lines on the diagram now meet at a right angle. The angle between the 2 lines is 90 degrees because I have equal scales. So let's look at a fact here. A horizontal line and a vertical line are always perpendicular. Doesn't matter where the horizontal and vertical lines are. The axes are perpendicular. The purple and green lines in this diagram are perpendicular. So that being said, let's start by looking at vertical lines. The first thing I want to do is go back to a number line. Let's plot the solution to x equals 5 on a number line. We did this quite a while ago. It's actually quite easy. There's only one solution to the equation x equals 5. That's the number 5. So all that we would do is put a point at 5 on the number line. I want to extend this to 2 dimensions. Here I'm asked to plot the solutions to x equals 5 in the coordinate plane. So I'm talking in 2 variables, 2 dimensions, x and y. Notice that on both of these problems, if all I had said was plot x equals 5, you might be confused. Are we talking about a point on the number line, or are we talking about something in 2 dimensions? So you need to know the context of a question like this. In this case, we've made it clear by saying plot the solutions to x equals 5 in the coordinate plane. So I need to think about solutions in an equation with two variables, even though I don't see a variable y in this equation, that satisfy the equation x equals 5. So in my table, I have a few values of y, -2, 0, and 3. I want to think about the corresponding x values that are going to satisfy this equation. Well, if y is -2, what does x have to be in order to satisfy the equation x equals 5? Well, x equals 5. If I use 5 for my x value, replace the x in the equation with 5, 5 equals 5 is true. What if y is 0? What would x have to be to satisfy the equation x equals 5? Well, once again, x has to be 5. And if y is 3, what would x have to be to satisfy the equation x equals 5? Once again, x has to equal 5. So let's plot these points. 5, -2, 5, 0. There's my point on the number line, the x-axis in this case, and 5, 3. What do we notice about these 3 points? Well, hopefully we notice that all 3 of these points lie on the same vertical line. So I'm going to use my straight edge and draw a vertical line connecting these 3 points. So in the coordinate plane, the solutions to x equals 5 look like a vertical line, whereas on the number line, the solution to x equals 5 was just the point 5 on the number line. In an xy coordinate system, the graph of x equals c, where c is a constant, is always going to be a vertical line with x-intercept c0. In this diagram, I have the vertical line x equals c in blue. C here is a negative number, since the line lies to the left of the vertical axis. And the horizontal intercept is c0. In this case, the x-intercept is c0. What's the equation of this line? Well, it looks like I have a vertical line, and we were just told that the equation of a vertical line is always of the form x equals c. So I need to figure out what is this constant c. Well, let's locate a couple of points on the line. Here's our x-intercept, -4, 0. At this point, you might know what the answer is. If you do, that's great. If you don't, think about some other points on the line. Here's another point on the line. -4, 3. Let's find one more. How about right here? -4, -2. What do all of these points have in common? The x-coordinate on all 3 of these points is -4. We're trying to figure out what constant x equals. That constant is -4. So we have the equation of the line x equals -4. So let's write our conclusion. The equation of this line is x equals -4. The y-axis also happens to be a vertical line. What's the equation of the y-axis? Well, we're thinking about this vertical line, the y-axis. So again, let's think about some points that are on this line. Here's a point on the line, 0, 4. Here's another point on the line, 0, 1. Here's another point on the line, 0, -3. What do all 3 of these points have in common? They all have an x-coordinate of 0. Remember, a vertical line always has equation of the form x equals c, where c is a constant. We've found that our constant here is 0. All of the points on the y-axis have an x-coordinate of 0. So the equation of the y-axis is x equals 0. Now let's look at another example. Plot x equals -9 and find the slope of the line. Since we have an equation of the form x equals a constant, we know that this is going to be a vertical line. The x-intercept of this vertical line is going to be -9, 0. So let's plot a vertical line through this x-intercept. Well, that's the first part of this problem. The second part asks us to find the slope of this line. So now that I have this line, let's think about the slope. This line has x-intercept 9, negative 9, 0, and another point on this line is negative 9, 5. Let's think back to our slope formula. To find the slope, we take the difference in the dependent variable, y sub 2 minus y sub 1, over the difference in the independent variable, x sub 2 minus x sub 1. So if I make my lower point x sub 1, y sub 1, and my upper point x sub 2, y sub 2, then I would have 5 minus 0 over negative 9 minus negative 9. 5 minus 0 is 5. Negative 9 minus negative 9 is the same as negative 9 plus 9, which is 0. I have 5 divided by 0. This should bother you. Division by 0 is undefined. So 5 divided by 0 is undefined. So we find out that the slope doesn't equal anything. The slope formula doesn't give us the value of the slope. It does help us, though. It lets us know that the slope is undefined. So we would say the slope of this line is undefined. In fact, the slope of any vertical line is undefined because vertical lines always have the same independent variable values, the same x values when we're working in an xy coordinate system. So when we take x sub 2 minus x sub 1, we're always going to get 0. Division by 0 is undefined. Now let's look at horizontal lines. Let's plot y equals negative 40 in the coordinate plane. I have an indication here that I have an equation in two variables, even though I only see one variable, y. I'm asked to plot this in the coordinate plane, and I see on my axes the variables x and y. So let's think about this. If I pick some x values, and I'm going to pick some based on the scales I see on these axes, negative 3, 0, 6. If x is negative 3, what's y going to have to be to satisfy the equation y equals negative 40? Well, y equals negative 40. So if x is negative 3, y would have to be negative 40. If we substitute negative 40 for y in this equation, we get negative 40 equals negative 40, which is true. What if x is 0? What does y need to be to satisfy the equation y equals negative 40? Well, once again, y has to be negative 40. And if x is 6, again, y has to equal negative 40. So let's plot the points indicated by the table. Negative 3, negative 40, 0, negative 40, and 6, negative 40. What do these 3 points have in common? They look like they all lie on the same horizontal line. So let's use a straight edge and connect these 3 points. So I have a horizontal line going through the 3 points in the table. In an xy coordinate system, the graph of y equals c, where c is a constant, is always going to be a horizontal line with y-intercept 0, c. In this diagram, I have a graph of a line y equals c. C is negative because c lies below the x-axis. Well, what's the equation of this line? Looks like I have a horizontal line. I was just told the equation of a horizontal line is always going to take on the form y equals c, where c is a constant. So I need to figure out what's this constant c. Well, let's locate some points on the line. Here's my y-intercept, 0, 3. Here's another point, 4, 3. And here's another point over here, negative 6, 3. What do all 3 of these points have in common? The y-coordinate is always 3. So that constant we're looking for in the equation y equals c, a constant, must be 3. So the equation of this line is y equals 3. The x-axis also happens to be a horizontal line. What's the equation of the x-axis? Well, when we're talking about the x-axis, we're talking about this horizontal line. Let's think about some points that are on the x-axis. The origin is a point on the x-axis. It has coordinates 0, 0. The point -5, 0 is on the x-axis. The point 4, 0 is also on the x-axis. What do all three of these points have in common? Well, it looks like in all three of these points, the y-coordinate is 0. Remember, horizontal lines always take on the form y equals a constant. We just see from our 3 points that the constant would have to be 0 in this case. In all three of these points, the y value is 0. So the equation of the x-axis is y equals 0. Now let's plot y equals -4 and then find the slope of the line. To plot y equals -4, the first thing I notice is I have an equation of the form y equals a constant. So this is going to be a horizontal line. In particular, it's the horizontal line that goes through the y-intercept 0, -4. So I'll start by plotting 0, -4, my y-intercept, and then plot a horizontal line through this point. So here's a plot of y equals -4. That's the first part of the problem. The second part says to find the slope of the line. Well, let's think about a couple of points on the line. We already marked one, 0, -4, the y-intercept. Another point we could consider is 6, -4. Both of these points lie on this line. Going back to our slope formula, the slope is y sub 2 minus y sub 1 over x sub 2 minus x sub 1. If I call the y-intercept x sub 1, y sub 1, and the other point x sub 2, y sub 2, then I have -4 minus -4 over 6 minus 0. -4 minus -4 is the same thing as -4 plus 4. That's 0. 6 minus 0 is 6. 0 divided by 6 is 0. The slope of this line is 0. In fact, we have talked in previous lessons about the fact that all horizontal lines have a slope of 0. The second coordinate in a horizontal line is always the same, in this case, -4. When we subtract the second coordinates, one from the other, we're always going to get 0 in the numerator of our slope formula. So finally, I want to look at a summary of slope. If we have an increasing line, as we do in this diagram, remember we always want to look at our lines from left to right. From left to right, this line is going upward, so it's increasing. We have a positive slope. All increasing lines have positive slope. For a decreasing line, again, read this line from left to right, it's going downwards. Decreasing lines always have negative slope. Horizontal lines always have 0 slope, and vertical lines always have undefined slope. Non-vertical parallel lines have equal slope. Perpendicular lines have opposite reciprocal slopes, provided that neither line is vertical. So let's look at a couple of examples for our final summary of slope in this part of the lesson. Can parallel lines have the same vertical intercept? Well, in this diagram, I've already been given a line. It looks like this line has a vertical intercept of 0, -3. Well, let's think about parallel lines. Parallel lines have to have the same slope. What happens if I think about lines that have the same slope as this line? Here's one such example. What about some other lines that have the same slope as the first line? There are lots of them. This one that has the same vertical intercept happens to be the same line. What if I move my lines to the left? It looks like, again, I'm changing the vertical intercept. The only time parallel lines could have the same vertical intercept is, in fact, if they were the same line. So then they would be the same line, not parallel lines. So we would say parallel lines cannot have the same vertical intercept. Well, let's look at another example. What about perpendicular lines? Can perpendicular lines have the same vertical intercept? Well, I already have a line on this diagram. It looks like the vertical intercept of this line is 0, 1. What do we know about perpendicular lines? Well, these are the ones that are a little bit tricky. The slopes of perpendicular lines are opposite reciprocals. So let's determine the slope of the line on the graph. Looking at a couple of points, it looks like I have a rise of 1 and a run of 3. So the slope of this line, rise over run, would be 1 over 3. The perpendicular line would have to have opposite reciprocal slope. The opposite of a positive number is going to be negative, so I know the perpendicular line is going to have a negative slope, and the reciprocal of 1/3 is 3. So the perpendicular line is going to have a slope of -3. Well, let's think about lines that have a slope of -3. There are all kinds of lines that I can draw in this coordinate system that have a slope of -3. But the question is, can it have the same vertical intercept as this line? Well, sure. If I start at the point 0, 1 and create a slope of -3, I can do that by drawing another point using, let's see, the fraction -3 over 1 reduces to -3. So a rise of -3 means down 3. A run of 1 means right 1. Down 3, right 1. This line should be perpendicular to the line given in the graph. The slopes are opposite reciprocals. Since the scales on both the r and s axis are the same, it should appear that these two lines meet at a right angle. Well, do perpendicular lines always have to have the same vertical intercept? Well, here's the lines that we started with the same vertical intercept, 0, 1. But can I draw other perpendicular lines to this red line that have a vertical intercept other than 0, 1? Well, certainly. There are lots of different lines that I can draw with a slope of -3. Here are some examples. So we see perpendicular lines don't always have the same vertical intercept. They can, as we saw on the last slide, but they don't have to. And so now I want to turn this over to Anne, who's going to talk about some applications of slope.
So in this final part of the lesson, we're going to talk about interpreting slope in the context of an application. Some of these problems are going to look quite different than what we've been doing with slope previously. But in all the problems, the underlying idea is going to be slope. We're going to start by looking at slope when we have data given in a table. Then we'll talk about slope when we have information given in a graph. And finally, we'll talk about slope when we're given a verbal description of a problem. So let's start with tables. Table 1 shows the unit cost for energy as reported by the U.S. Department of Energy from 1995 through 2000. The unit costs are given in dollars per million BTUs. Well, that's an awfully odd unit cost, so let's think about BTUs. BTUs is an abbreviation for the British thermal unit, and this is the standard measure of heat energy. All energy is heat energy. It takes 1 BTU to raise the temperature of 1 pound of water by 1 degree Fahrenheit at sea level. Well, that's kind of abstract. For example, it takes about 2,000 BTU to make a pot of coffee. So with 1,000,000 BTU, we can make 500 pots of coffee. So when we think about 1,000,000 BTUs, let's think about the energy we need to make 500 pots of coffee. So here's the table, and we see, let's look at the table a little bit, see what we see here. We see that indeed, we have the years from 1995 through 2000, and we have our unit cost of energy, given in dollars per million BTUs. So in 1995, it cost $8.25 to buy the energy to make 500 pots of coffee. Let's kind of look at this table globally to see what's going on. We see that the unit cost increases a little bit, increases a little bit less, decreases, and then going up again. And finally, there's kind of a big increase between 1999 and 2000. The data in this table definitely does not describe a linear relationship, but we can still talk about slope. Let's first look and decide between which 2 years did the cost of unit energy change the most. Well, from our glance at the table previously, we saw that from 1999 to 2000, the unit cost of energy increased the most. Let's focus on this increase. What is the average rate of change between these 2 years? Well, remember, slope is a rate of change. So we can think about slope when we're just looking at these 2 data points and talk about the average rate of change. Let's give ourselves some room to work. So here I'm just looking at the last 2 rows in my table, and I want to calculate the average rate of change. That is the slope between these 2 data points. So calculating the slope, I'm going to take the change in the unit energy cost over the change in the year. So we have dollars per million BTU per year. That's quite a rate, but that's what we have. So doing the calculation, we see that the average rate of change in the unit cost of energy between 1999 and 2000 was, and let's see, 985 minus 830, oh, it's 834. Let's see, that is $1.51. So that's $1.51 per million BTU per year. So the data in our table was not linear, but we can still talk about average rate of change from one year to another. We're talking about slope. Now let's look at slope determined from graphs. We've done this kind of problem before, but let's look at a problem, an application problem. Anton and Mobutu are running at the track. Anton was late, arriving 10 minutes after Mobutu started. Figure 1 shows the distance d measured in meters each runner has covered t minutes after Mobutu started running. We're measuring time since Mobutu started running because Mobutu showed up on time. We want to determine the slope of each line and state the practical significance of this slope. So here's the figure. So we can see on the horizontal axis that we're measuring time since Mobutu started to run. Mobutu's run is given to us with this blue line. Anton's run is given to us with this more reddish brown line. The vertical axis shows the distance they've run in meters. Now we can see that Anton started a little bit late because the point 10:0 is on the graph. So 10 minutes after Mobutu started, Anton's distance was 0. That's when he got to the track. But they asked us to find the slope of each line, so let's do it. So let's determine the slope of each line by finding a couple of ordered pairs on the lines. Let's start with Mobutu's run. I see that the origin is on the blue line, and it also appears that the ordered pair 50, 9,000 is on this line. So when I calculate the slope of the blue line, which represents Mobutu's run, I'm going to look at rise over run. Well, I rise 9,000 meters and run 50 minutes. So I have 9,000 meters per 50 minutes. 50 goes into 9,000, let's see. 5 goes into 90 18 times, so 50 goes into 9,000 180 times, so the slope of the blue line is 180 meters per minute. Let's look at the red line, which represents Anton's run. We have the ordered pair 10:0 on this line, and we also have the ordered pair 50, 10,000. So calculating the slope of the red line, we're going to think about rise over run. So the rise is 10,000 meters. The run is 40 minutes. We're going from 10 minutes to 50 minutes. So 10,000 meters per 40 minutes. And if I divide 40 into 10,000, 4 goes into 125 times, so 40 goes into 10,000, 250 times, so I end up with a slope of 250 meters per minute. So now let's state the practical significance of these slopes. Well, meters per minute is a measure of speed. So the slopes of these lines are telling us about how fast Anton and Mobutu are running. So the slope, m sub r equals 250 meters per minute, tells us Anton is running at a speed of 250 meters per minute. The slope m sub b equals 180 meters per minute tells us Mobutu is running at a speed of 180 meters per minute. Now we want to kind of look at these speeds and look at the graph a little bit more closely. What we notice is that the slope of Mobutu's line is less than the slope of Anton's line. Mobutu is running more slowly than Anton. Anton arrives late and he starts running quite a bit faster than Mobutu. We see that the line that represents Anton's run is steeper than the line that represents Mobutu's run. There's a bunch of other questions we can ask in the context of this problem. For example, let's think about the practical significance of the point of intersection. The coordinates of this point I can estimate from the graph. The coordinates of this point seem to be about, let's say, 38 6,900. What does this tell us in practical terms? Well, that point is on both lines. So the time, 38 minutes, is when both runners have run 6,900 meters. So the point, 38, 6,900, tells us the two runners have run 6,900 meters, 38 minutes after Mobutu started his run. Remember, at this point of time, Anton's only been running for 28 minutes. So now let's think about this. If Anton ran the same pace as Mobutu, how would the graph change? Well, if Anton is running at the same pace as Mobutu, the slopes of the two lines would be the same. And lines which have the same slope are parallel. Let's take a look at what happens. Notice the two lines no longer intersect when they're parallel. What did the point of intersection tell us? It told us that there was some point in time where Mobutu and Anton have covered the same distance on the track. That no longer has happened. So if Anton and Mobutu agreed to run until Anton caught up with Mobutu, would this now be possible? Well, the answer is no. There is no one moment in time when Anton will have gone the same distance as Mobutu. So no, this is no longer possible. Since the two runners cannot cover the same distance in a given time since Mobutu started running. The only way Anton is going to catch up is if he goes at a faster speed. Let's look at one final example. A building inspector measures a wheelchair ramp. Her measurements are shown in Figure 2. We want to find the grade of the ramp. So what's the grade of the ramp? The grade of a ramp is a measure of its steepness, usually expressed as a percent. So the steepness of the ramp is going to be the slope of the ramp, the slope of this line in my figure representing the ramp. So that's going to be rise over run, 3/30. So let's find the grade of the ramp by calculating its steepness, its slope. Well, the slope is 3 feet over 30 feet. The units in this situation cancel, so this is just 3/30 or 1/10. This is why we can write grade as a percent. 1/10 is 10%. The grade of the ramp is 10%. But the building inspector is not happy. The inspector informs the owner of the building that the city requires at most an 8.3% grade. They have a 10% grade. We want to find the minimum horizontal distance from the start of the ramp to the building to comply with city regulations. Let's look at our figure again. In our figure, we currently have a horizontal distance of 30 feet. We want to decrease the grade of the ramp, so we're probably going to want to increase this distance. Let's call this distance x now and figure out what it should be so that we have an 8.3% grade. So I'm going to let x represent the horizontal distance and I'm measuring distance in feet in this problem from the start of the ramp to the building. Now I definitely need some more room here to solve the problem, so let me get rid of my figure. So I know that the slope should be at most 8.3%. So let me figure out what distance is going to give me a slope of exactly, or a grade of exactly 8.3%. So the rise to the run needs to be equal to 8.3 out of 100. Well, this is just a proportion. We can solve this proportion by cross multiplication. 8.3 times x should equal 3 times 100. So 8.3x equals 300. So x is going to equal 300 over 8.3. Let's pull out a calculator and get a number. So 300 divided by 8.3 equals 36 point yada yada yada. Now, I want to make sure that the ramp is long enough to comply with the city regulations. If I build a 36-foot long ramp with a horizontal distance of 36 feet, the grade might be too high. So here, I'm going to round up rather than round down. So the minimum distance that I would measure would probably be 37 feet in order to get a grade that complies with the city code. So the minimum distance should be about 37 feet. So that's a very different application of slope than some of the other applications we've considered in our introductory examples. So that finishes lesson 15. In our next lesson, we're going to talk about graphing linear equations.